In this tutorial, we'll be looking at the dynamics of objects on inclined planes. I've taken the time to draw some object here. It's denoted by this red box, and it's free to move up and down the plane. So I've placed a coordinate axis to go right on top of it, which I've drawn here in green. And let's go ahead and start by making a free body diagram of the different forces acting. Of course, we have a weight vector going downwards, and so that's going to be mg. We have a normal force, which is always perpendicular or normal to the surface, which I'm going to draw in as F sub n. And if there's friction acting on the incline, it's going to be going up the incline, as the tendency for this object is to go down the incline, assuming no other forces are acting on it. You'll see that now the normal force and the frictional force are in the second and first quadrant respectively. And typically what's done for these types of problems is that the entire coordinate axis system is rotated. So if we take the time to actually redraw our coordinate axis system here, we'll see now that our free body diagram ends up as having only one of the three forces which needs to be resolved. And so now that switches, since we've rotated our coordinate axis, that switches the weight vector now needs to be resolved into its x and y components. This is our new x-axis, which I'll label here as x. Our new y-axis is there since we've rotated it. And I should now see that I have an x and a y component of the weight vector. I'll draw in mg in the y direction, and I'll also draw in over here mg, or the x component of the weight vector. What that means now is that I need to know some angle here that the weight vector makes with one of our axes. In this case, it's going to end up being the y-axis. And we're going to find out that through some geometry that it's the same as the angle of inclination. So again, the angle that this weight vector makes with the y-axis is the same as the angle of inclination. I'll show you how that works just through this quick kind of geometry. What we'll see is if I draw a weight vector going straight down, I'm going to do this just a little bit larger just to prove a point. We'll see that the angle theta, and I'm going to draw your attention kind of to this triangle right here that I'll kind of shade in green. We'll see that this triangle right here has theta, a right angle down here, which, since we know that the sum of the interior angles needs to be equal to 180, then this unknown angle right up here is going to be the complement to theta, which I'll draw in as beta. It doesn't matter, and I'm going to just use a different color so we can see that a little bit more clearly. And since we also know that the new rotated x-axis and y-axis are perpendicular to each other, then this angle must be the complement to beta. So it again then becomes theta. So this is an important realization when you're doing the problems with dynamics on objects on inclined planes. And so it's important to see now that this angle theta is made with the negative y-axis is the weight vector. Since we're referencing the y-axis now, that's going to make some changes to our typical x and y components if I were to kind of redraw this axis over here off to the side. So I now have the same coordinate axis that I've rotated so that the x-axis is parallel with the plane. My weight vector, which I'll draw as a dashed line, is going downwards. That's mg. My x component of weight here and my y component of weight here. Notice I could draw the x component of my weight vector as the opposite side of this angle theta, and I could say that the y component, or the vertical component, would now be the adjacent side. What that means is when you're dealing with an object on the inclined plane, because you've referenced the y-axis with the angle theta, to find the x component, or the parallel component of the weight vector, is going to be the original weight vector mg times the sine of the angle theta. And that's different from what it typically is when objects are not on inclined planes. Usually to find the x component of the vector, you would multiply it by the cosine. So now we just found the x component by multiplying the original weight vector mg times the sine of the angle theta, which is made with the y-axis. And that's because it's referencing the y-axis here. If it were referencing the x-axis with the angle theta, then we would use our typical mg cosine theta to find the x component. For the same reasons, we'll then see that the y component of the weight vector becomes mg cosine theta to find that vertical component. So if the object were on an inclined plane, as I've drawn here, and it were not moving, I could say then that the sum of the forces in the x direction must be equal to 0 since it's not moving, and therefore up the incline, which is positive, in this case would be friction, minus the parallel component of the weight vector mgx must be equal to 0, since that vector has to have the same magnitude as that vector, since the sum of the forces must be equal to 0. If I were to kind of add mgx to both sides, I would see here that friction is equal to mgx. And now I'm going to substitute both of these terms for friction. I'm going to get mu static, the coefficient of static friction, times the normal force, is equal to mg times the sine of theta. Times the sine of theta. In the y direction, I can say the same thing, that the sum of the forces in the y direction is equal to 0. Again, the evidence for that is that it's not accelerated. In this case, it's not even moving. And so that the positive force, in this case, which would be the normal force F sub n, minus the negative, plus the negative mgy, that should be a y, is equal to 0. And therefore, I can say that the normal force is equal to mgy, or mg cosine theta. Most of the time, not all the time, but most of the time, most of the time, we're going to make a substitution. Let me change this to red. We're going to make this substitution right here, and that is the normal force gets substituted in for the x direction. And so my final expression would look something like this. And I'm just going to continue this on over here in the lower right-hand corner. Mu static times mg cosine theta is equal to mg sine theta. And really, depending on what you're looking for, what you're solving for in this problem, you could algebraically maneuver to isolate the unknown.